All right, so welcome to today's video. Today we're going to be talking about transparent huge pages. And to give you an idea of where this came from, let me give you some background. So, as you can imagine, Nanos, the Unikernel, has been out for years. We've had not just users, but customers in production for years now. And so we show up in research papers like this one, are Unikernels ready for serverless on the edge? And so anybody writes a paper like this, I end up reading it. And I go through, and if they mention us, I pay even more attention. And so this one in particular found about, I don't know, 4 different issues that we ended up looking into. One actually was fixed before this paper even came out, because I guess they wrote this, let's see, a little over a year ago. I found out about this maybe January or February. It was published in March, or I guess that's a preprint. But anyways, found about 4 issues. One of them we already fixed. One of them wasn't an issue. One of them we fixed after we found out. And then there's another one that we're talking about today called transparent huge pages. But basically, what the deal was they're wondering why memory utilization kind of, in their terms, memory performance was so bad compared to some of these others. And we kind of took a look at it, and we quickly kind of found out that it was because many of these other systems had transparent huge pages. So let's get into that. What does that actually mean? Well, when a program starts to allocate memory, they allocate it in chunks of 4K. And so for well over a decade, Linux has had this capability. Started out with huge TLB, and then it morphed into what's called transparent huge pages. And basically, you can allocate at 2 meg chunks instead. So that's a really, really big difference. And it makes a even bigger difference, when you start getting into like gigs of heap and so forth, because these get stuffed into a cache, and if the cache gets missed, then you got to go do a more expensive operation. And anyways, it's just this like cascading performance fail. And it's one of these features that we just didn't even like really notice in Nanos. It's not the first feature like this that it's been a while that we just for whatever reason skipped it. But anyways, we threw it in. And so by default now with this PR, you'll see it running by default. You can disable it, of course, but by default it's on. So we hunted down this paper to see how they were benchmarking it, and they were basically doing something of this nature. This Alloc test basically allocates about 50 megabytes, and then it walks through page at a time, which is 4096 4K, and it touches it, each page. And the idea here is to by touching each page, we should be able to page fault out at that page size granularity, right? And that's actually what causes the performance issue. And you can actually measure this too. If you're running it, we can actually literally see these faults happen. But that's what this test is designed to do, is to kind of force that to happen. Okay, so let me just show you what running it normally without this optimization does. Okay, so it says elapsed 18 milliseconds. Okay, not so bad. I mean, it's 50 meg, takes 18 milliseconds, give or take. And we left the server on just because we wanted to slap it a couple of times. It makes it easier to kind of like, get some averages, get some P99s, that sort of thing. However, let's go ahead and try it with this guy. So we're going to do ops run php, and this time we're going to specify the Nanos version of this pull request, right? So all you got to do is take the hash of whatever commit you want. These stay up for about, I think it's 20 or 30 days. Hopefully by that time we've merged in the PR. If not, well, maybe we'll make another commit. Anyways, you take that and we run it again. Look at that, 7 milliseconds compared to 18. And we see this play across, and you can just run it again. We see this play across like lots of different languages. And yeah, it works in Go and so forth, but okay, so let's check out Java. Let's see how it performs in Java. So we have this hello Java. I tried to do more or less the same thing. We go ahead and do 500, and then again we walk the 4K array and tag it. We time it, and then I'm also grabbing the memory just to kind of see, to ensure that it gets the right stuff, right? So let's go ahead and run it. First, I'll run it without. Okay, so it says 198 milliseconds. All right, and then let's run it with the Nanos version. All right. Okay, that was noticeably faster. I don't know if you saw that. I mean, obviously I'm logging it, right? But let's just run the difference again, because you can actually notice it. That's how much faster it is. So 200 milliseconds, 195 milliseconds. And we pop this guy back on. Boom, 81, 82. So it's noticeably faster. You're going to see a lot more performance improvements in things like Java, in things like Python, Node.js. I haven't even looked at that yet, but I know it's going to be the case. Pretty much any of your interpreted languages and any of your bytecode based languages are going to get a pretty big performance boost from this. Some things that you might want to not have this on are databases. A lot of databases, especially like older databases, they're tuned kind of not to have this. So if you go to like PingCap, or you go to MongoDB, or you go to some of the Postgres vendors, they'll explicitly tell you to turn it off, and that's just because the database is built with its own like memory allocation. But if you're running like a web server or something like that, you most definitely want this on. All right, till next time, catch you later.